Hi, everyone. So today we're going to talk about friction and introduce power. So first, we're going to derive the equation to calculate the work done by a friction force. So friction has its own equation for work, similar to springs, right? Springs also have their own equation for work. So if we look at the friction force, right, that is mu times n, right, the fun equation. The work done by friction is called the wonderful equation. You take the mu n and then you multiply it by the distance that an object travels while rubbing against that friction surface. Now remember, this is distance. So friction will actually take into distance, not displacement, but that's a different conversation we'll have another time. So that's the equation we'll use. We have a 6 kilogram block that is initially at rest, is pulled to the right by a constant horizontal force of 12 newtons along a rough horizontal surface with a coefficient of kinetic friction of 0.15. So let's draw this real quick. We have rough surface with a mu k of 0.15. We have a block with a pull force of 12 newtons. There is a friction force. It is a mass of 6 kilograms with mg and normal. Is that everything we had? Okay. So first, it wants to calculate the speed of the block after it has moved 3 meters. Okay, so we have a delta x of 3 meters. So what we'll do to solve this is we will use the work kinetic energy theorem. We'll take the summation of work, and then we will use that summation of work to find kinetic energy. Let's start here. So we have summation of work. We just went in the x direction because that's the direction of the velocity. That's the anything perpendicular to the direction of the velocity is not going to contribute. So we will have the work of the pull force minus the work of the friction force. So we have the work of the pull force is just FD cosine theta, but cosine theta of 0 is 1, so we'll just do F times D. So we've got 12 times 3 minus mu ND, but here N equals mg, and it will in a lot of our problems. So you can use mu mg times the distance. So we will say we have 0.15 times the mass, 6, times gravity, 9.81, times our distance, which is 3. So that will all come out to 9.51 Newton meters. Okay, that is the summation of work going into the work kinetic energy theorem. So if we do work kinetic energy theorem, we have the work equals delta K, which is 1/2 m v final squared minus v naught squared. Starts at rest. We have that right there. So that goes away. And all we want is v final. So if we take 2 times the work divided by m, all under a square root, we get v final. That would be the square root of 2 times 9.51 divided by 6. And this gives you a velocity of 1.78 meters per second. So that's how we can find the velocity of a block rubbing on a horizontal surface. Now I do want to show you this real quick. If we take 2w over m under a square root, okay, we can also look at this if we did summation of forces. Okay, imagine we do summation of forces on this free body diagram, and instead of finding the summation of work, we divide that summation of forces by mass to get the acceleration. Then we can use that acceleration to find our v final using our third orange. Third orange is v final squared equals v naught squared plus 2a delta x. if our V naught is 0, then V final is the square root of 2a delta x, right? Now let's look at work real quick. Work is F delta x cosine theta. Well, let's ignore the cosine theta for this part because we're just looking at comparing this to this. So if we have F times delta x, but under the square root we divide work by mass, let's divide this by mass. Force divided by mass is acceleration because of F equals ma. So if you take 2 times work divided by mass, you really get 2a delta x. So you can see that these two go hand in hand on that one. So it does work if you use summation of forces. Usually work is going to be faster. In this scenario, I'd say that they're kind of the same. On the next problem, you definitely want to use work instead of summation of forces. But you can go both ways on some of these when you're trying to find velocity. Work kinetic energy theorem is not the only way to solve it. You can also use summation of forces. There's always more than one way to solve a physics problem. Okay, next, in general, should we sum on part B, should we sum at the force or work level? Well, you want to sum at the work level, okay? Because if you have a summation of work, okay, equals FD cosine theta for many different forces, you don't want to take the summation of force, multiply it by the distance traveled, then just some cosine theta. That can get hairy because this theta is specifically the angle between force and displacement. But that theta does not apply if you just do summation of force. You just stick your summation of force number in there. You don't know what theta to use because maybe not all of those forces had the same angle with regards to displacement. So if you do that, that's not actually going to work. You would have to find each individual work done by each individual force, then sum it up to get your summation of work. So don't sum at force level and then just do d cosine theta. It's not going to work. Might work sometimes if you get lucky. Now, one more problem with friction. So here we have a block of mass 2 kilograms is attached to a spring that has a K constant of 500 newtons per meter. The block is pulled 5 centimeters to the right and 5 centimeters to the right of equilibrium and is then released from rest. So we have this picture up here to go off of, right? Pulled 5 centimeters and then you release it. So you've elongated the spring. Now find the speed of the block as it passes through equilibrium if the coefficient of friction between the block and surface is 0.35. So let's get our givens. Okay, we've got a mass of 2 kilograms. The K constant is 500 newtons per meter. Our delta X is 5 centimeters, so we'll call that 0.05 meters. It's released from rest, so V naught is 0. And our coefficient of kinetic friction is 0.35. Okie doke. So that's what we have. If we are going to do summation of work, okay, it would be helpful if we had a free body diagram. So let's see, we've got the force of the spring going this way. You're going to have the force of friction opposing you, okay, and then you'll have your mg and your normal. So our spring is now actually the positive work, as you can see in that image, and then friction is going to oppose us. So let's go for it. You've got the work done by a spring minus the work done by friction. Now remember, the work done by a spring is 1/2 kx squared. And the work done by friction, the wonderful equation, you have mu and d. Well, in this case, d is delta x. So you can substitute that d out for x so that everything is in the same terms, right? We've got x there and x there. Just kind of keeps things consistent. We also know that mg will equal normal force because we were on level plane, so we can take out that normal force and put in mg. So we have mu mg times x. Now I believe we have all those numbers: 1/2 k x mu m g and then x again. We've got all of it. So let's plug all that in. We've got 1/2 times 500 times 0.05 squared minus 0.35 times 2 kilograms, 9.81, and 0.05. Okay, that will come out to, so if we solve that, that comes out to 0.28165. That's excessive units, but we'll stick with it. Now, if you want to find we want the speed, right? So we would take work equals delta K, which is going to be 1/2 m v final squared minus v naught squared. But again, starting from rest. So we actually have the same equation as last problem: 2 work over m equals v final. And if you plug that in, you will get 0.53 meters per second. All right, so that is the velocity that we get as the object passes through the spring's equilibrium. Now, what changes if we put this system on an inclined plane? Well, it says specifically the block is pulled 5 centimeters to the right of equilibrium. It doesn't say that it's stretched or compressed, just 5 centimeters to the right. So if we have these two different scenarios, right? We have the block, spring, inclined plane, right? But it is pulled 5 centimeters to the right. So that means that if we look at our mg, right? mg will actually have some work contributing to this problem. You can see here that this is along the same direction as displacement, so you will have positive work, right? It's in the same direction. mg will actually help the block slide down the incline. Now let's look at if we had an incline going the other way. If we have, say, a block here, spring, 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 but it is pulled 5 centimeters to the right, that would actually compress your spring, which means that if we look at mg here, mg will still have this segment contributing to the problem. It will be in the same direction, or I guess in the same dimension, along the same axis, but our block is going this way. So here you actually have a negative work done by mg. So if we have an inclined plane, that's going to incorporate a new force on our summation of work. But don't worry, inclined planes are going to come up. That always happens. You would just either add or subtract that component of mg's work to change that. All right, now this slide is mostly relevant to our school. In Physics 1, we have a lab where we run up the bleachers at the stadium. We have the measurements and everything, and we just time each student, and depending on their time, we can calculate their horsepower, and we have a competition of who has the most horsepower in the class. So it's really fun. But this is kind of a callback to that. We will introduce power using a similar example. Okay, we've got 2 students, Bill and Ted, going on this excellent adventure while they run up the stairs, and they stop at the same position. Okay. Now, we will look at who does more work, who generates more power, and who has the more excellent adventure. So if we have the work, okay, work is mg delta y in this case, right? because work is going to be FD cosine theta, right? The distance they're traveling is going to be something like their delta y. But they are going on the same staircase, so cosine theta doesn't matter. If we're comparing their work, they also traveled the same distance, right? They stopped at the same spot, stop at the same position, so that doesn't matter. They're doing it on the same planet, so we assume gravity is going to be the same. So the only thing we are really comparing is the mass. That's the only difference between the work that they were doing. So if we look at the mass of Bill and the mass of Ted, the mass of Bill is actually double the mass of Ted. So that would mean that the work of Bill is double the work of Ted. So that means that Bill does more work. Bill wins. Now, who generates more power? Well, let's talk about power. Power can be found by doing work divided by time. Now, if we look at the time it took Bill to get up the stairs and the time it took Ted to get up the stairs, again, we have the time of Bill is double the time of Ted. But if power is work divided by time, let's look at the power of Bill. Well, if we're just comparing masses because nothing else in the work is actually changing, we have the mass of Bill divided by the mass of Ted. I'm sorry, no, that's not right. We have the mass of Bill divided by the time of Bill. And then if we look at the power of Ted, we would have the mass of Ted divided by the time of Ted. Those are the comparison points. So if we put everything in terms of Ted, this would be 2 times the mass of Ted divided by 2 times the time of Ted. But those 2's will cancel, and it looks like Bill and Ted generated the same amount of power. Now you can look at it in 2 different ways. We can look at it from Bill's perspective. Okay? If Bill did double the work, but it took him twice as long to do it, that diminishes his power. Also, if we look at Ted, if he did half the work, but he did it in half the time, so he wasn't working as hard, but he did it twice as fast. So that's all going to kind of cancel out, and you're going to see that they actually end up doing the same amount. They generate the same amount of power by doing different amounts of work depending on how long it takes them to do the work. Okay? And then who has the most excellent adventure? I would argue that that is Ted, because Ted equals Keanu Reeves. All right, so that's what we have for friction and power. Our next video is going to just go over a couple power problems and a power paradox.